Let's get back to Feynman's crazy way of doing quantum mechanics. So, according to Feynman, anytime a particle, a photon, or even a macroscopic object moves from point 1 to point 2, it has some chance to take any path. And as preposterous as it might sound, he found that we need to include all these paths in our calculation, where each path is weighted the same. So why then do we not see all those crazy paths? Well, that's because we still need to add up their amplitudes. For simplicity, imagine we only have 3 paths. Then here's what we're going to do. First, let's take this one. When the particle wave starts following it, we start a stopwatch. It goes around and around very fast, and when it gets to the end point, we hit stop. We'll do the same for the other 2 paths. And then we add up the arrows, square the result, and that is then proportional to the probability the particle took those paths to get there. In this case, the arrow and square are pretty small, so the probability of the particle going from 1 to 2 using these paths is small. Compare that with these 3 paths, for example. Well, now the arrow is much larger. And this is important. The larger the resulting arrow, the higher the probability of that event happening. Now, in these examples, the stopwatch is not actually measuring time. Instead, it measures something called the phase. Just as in the double slit experiment, when a wave takes a different path from point 1 to 2, it will end up there with a different phase. And this phase is what determines the amplitude of the wave at that point. Mathematically, we can write the amplitude, our stopwatch, as e to the I phi, where phi is the phase. As the particle wave follows a path, its phase increases, winding the vector around. So now the big question is, how much does the phase change for each path? Well, to answer that, imagine we split up the path into many tiny sections, each one so small that it's effectively straight. Then, in each section, the particle wave goes a distance delta x in a time delta t, and the increase in phase is easy to compute. It just depends on the wavelength and frequency of the wave. To find the total increase in phase for the whole path, we just add up all the little phase increases of all the individual sections. But we can sub in lambda equals h over mv from de Broglie, and using E equals hf, we can sub in for frequency. We can also simplify by writing h over 2 pi as h bar to get this expression. Then we can take delta t to the right, and if we make delta t infinitesimally small, then we can replace this sum with an integral. But now dx by dt is just velocity, so we can write this as mv squared. Now, we know that in the simplest case, the total energy E is just kinetic plus potential energy. And subbing that in, we're left with the integral over time of kinetic energy minus potential energy. But wait a second, that is just the classical action. So it's action that determines how fast the stopwatch turns. As the particle moves along a trajectory, its action increases, and that is what increases the phase. And what's important to note is that h bar is tiny. It's about 10 to the minus 34 joule seconds, which is way smaller than the action of any everyday object. That means the phase of ordinary objects on ordinary paths spins around zillions of times, eventually pointing in some random direction. If you consider a slightly different path, the action may be slightly different, say 0.01 joule seconds different. That doesn't seem like much, but divide it by h bar, and the arrow will spin around 10 to the 32 more times, so again, it will just point in some random direction. This is what happens to almost all of the possible paths, so when you add up the phases, they just cancel out, they destructively interfere. The only exception is for the paths closest to the path of least action, because these paths are at a minimum. So if you make tiny changes to the path to first order, the action doesn't change. And so for other paths that are very close to the path of least action, their arrows point in basically the same direction. They constructively interfere, And